So this is not my favorite version of what intensity is. And in fact, on the very next page, I think that's actually the version that I like the most. So I'm going to go ahead and recopy it back over here. I don't like to think of it that way. I like to think of it as intensity is power per unit area. Anybody remember what power is? Yeah, it's work per unit time, right? It's how quickly you can do work. So that's essentially what power is. What do we measure work in? What unit? Not watts. Huh? Joules. Joules. All right. And then so power would be a work per second, which would be a joule per second. And what do we call that? What was that answer I got over here a second ago? A watt. So the power is the watt. All right. So if you ever see that on like a light bulb or something, it's telling you how much energy per unit time it is using, watts. Okay. And yeah, and then the voltage is something different. When we get into that voltage stuff, we'll talk about that too. So this is what intensity is. Intensity is the amount of power you have per unit area, right? If you get really close to a light, it's very bright in your eyes and can hurt you. If you're way far away from it, it gets to be much more dim and less of a big pain on your eyes. Why is that? It's not because the light coming from it is losing a bunch of energy as it goes towards you. What's happening is it's spreading out as it goes towards you. And in fact, it usually spreads out spherically. Not always. We can do something where that doesn't really happen, like in a laser light or something. It doesn't quite do that, but it spreads out spherically, right? Like if we had a flash bulb and it went off, it would spread out spherically. And so that energy, if we had it just go off in a single instant, would start spreading out, and it would start to get weaker and weaker per unit area because it gets spread out more and more. Think about a balloon. Anybody ever grab like a red balloon and you blow it up? Does it stay that dark red color? What happens to it as you blow it up? It gets lighter in color, right? Because you don't have less of that red pigment, you just have it getting spread out more and more over a greater surface area. And that's the same sort of thing that we're interested in here. We're not interested in the total power from the sound. We're interested in the amount of power there is per unit area where we're interested in looking at it, right? Put your ear right up to a speaker, blast your eardrums up, go to the other side of the room or the other side of the field or something like that, and it's a lot less, it sounds a lot less loud to you, right? And that's because that intensity has decreased because it's spread out more and more over a greater and greater area, and that's that power per unit area. So as it spreads out over a greater area, that area gets bigger, the power is the same, but the area gets bigger, and so therefore the intensity gets to be less and less, because essentially less of the energy makes it down into your little ear canal and into your ear. When you're up close, a lot of it gets in there. When you're far away, it's spread out so much that you don't get as much of it straight directly to you. And this you can even think of for things like gravity and stuff like that. They all spread out spherically. And so you get that same sort of thing, okay? And so you're interested in how it's spread out per unit area for intensity. And there it is. And it's a watt per meter squared. The watt is the SI unit for power. And then, of course, areas are measured in area or length squared, in which case we use meters for SI unit for length. So watts per meter squared, all right? You can think of it almost as like a density, a power density, right? Per area instead of a per volume, like an areal density, okay? And if you go back here, it's energy per time right there. This E over T is just power, right? So that's why I'll prefer that power over area one more. It's just the way I think of it, power per unit area. Here, if you're going from point source and we're going out in that spherical symmetry, you can see that the area is going to be that 4 pi r squared. What is 4 pi r squared? not area of a circle, not volume of a circle. It's r squared, can't be a volume. Not circumference. No, can't be a volume. It's surface area. There you go. It's an area. It's surface area of a sphere, right? That surface area of a sphere, 4 pi r squared. Oh, we got to work on our geometry, right? So 4 pi r squared, surface area of a sphere. You let this sound out and it starts off on this very small sphere and everything is very intense on this very small sphere. And as it spreads out over larger and larger spheres, right? And so if you double the distance, you're going to cut the intensity to 1/4 of what it was because it's a 1 over the distance squared. Okay? So double your distance from a sound and you get that double, it gets a 2 on the bottom, it gets squared, you have 1/4 the intensity of what you had before. And that's that 4 pi r squared. In fact, that 4 pi r squared shows up a lot in physics because we have, we have that spherical symmetry in our space around here. I think y'all said you didn't do this, but maybe you did it in another one. G m1 m2 over r squared. We recognize that? Anybody from any past physics courses? It's a shame. We wish we would do that, but that's Newton's universal law of gravitation, right there. So that's the force of gravity between two objects, mass m1, mass m2, and with a separation between them, between their centers of r. I said this should be 4 pi r squared. Where's the 4 pi? That's great. It's in the G. G is the universal constant of proportionality. It's inside of there. So whatever it was, you just divided it into 4 pi and combined it into that one constant. But the 4 pi is in there. When we do electrical fields and electric forces, we'll actually get this one. It's written a lot as this way, Q1, Q2 over R squared. And this is called the Coulomb constant. Sometimes it has a little C down at the bottom for the Coulomb constant, the guy that came up with this. And then a lot of other times it's written as 1 over 4 pi epsilon naught Q1, Q2 over R squared. And there you see the 4 pi R squared. So in this version right here, the 4 pi is not absorbed into the constant. If you absorb this all into one constant, they call it the Coulomb constant, but it's right there. And so this shows up a lot when you have this spherical type symmetry, okay? You don't need to know those. Oops, I thought that was the eraser. But just showing you, it does happen a lot when you have spherical symmetry, which we seem to have a lot in space and everything, okay? Next, sound intensity. Bats can use this decrease in sound intensity to locate small objects in the dark. All right, so they can bounce sound off of something and then based on the intensity that comes back, you know, judge distance. And then of course the direction that it came from, they can judge, you know, where it came from. So it's pretty interesting that you only have 2 ears, but yet you can 3-dimensionally tell where a sound came from. And if you go think through that, that shouldn't quite be possible, right? Because if you should only be able to tell the difference between those 2 ears, and it should give you like a location on a circle, not a single point, but we can tell a single point. So, you know, you biology people, you ought to look into that. It's pretty interesting stuff. I won't go crazy with it here, but yeah, it's really neat that we have we can locate a sound based off that. So, and they can do the same thing. They can locate a direction and then of course a distance based on what the intensity was. Here, sound intensity and how we hear it. It turns out we don't quite hear sound intensity like it is. If we double the intensity of a sound, we don't quite hear it as being twice as loud. All right. In fact, it turns out that our hearing is actually pretty logarithmic for what we interpret hearing or loudness to be. And so, like it says here, when you listen to a variety of sounds, a sound that seems twice as loud as another is 10 times more intense. What is that? Okay. So just keep that in mind. If a sound starts to hear twice as loud to you, it is 10 times as intense as it was. Okay. So that's a very big difference. So what we use here is a logarithmic scale, and we call this decibels. And it's the decibel here, and that's that beta that's right there that we use as the intensity. Notice it is 10 times the log of the intensity of the sound divided by a reference intensity. You can set this reference intensity to be anything you want, but most common for the decibel scale is to set it at the threshold of human hearing, the softest, lowest intensity sound that we can hear. All right, you can also notice that it tells you here this SI unit is none. It's a dimensionless thing because we essentially just have we have just intensities over intensity. So all the watts per meter squared are going to cancel out, and it's essentially a ratio. So it's the log of a ratio of things to tell us how loud something is compared to that. So if I tell you, this is the interesting little part here. Let's look at it right here. All right, so on this decibel scale here, we can see that what happens is every time you increase by 10 of these decibels, you end up with 10 times as loud of a sound, or 10 times the intensity. So that means if I look at something like 50 to 60, so a classroom versus a conversation kind of thing, really feel like those should be reversed. If it's like elementary school, I've seen my wife's elementary school classes, they're very loud. But if you go from 50 to 60 decibels there, you're actually 10 times as loud at 60 decibels. What if you go from 50 to 70? How much louder is it? 100. A lot of people make a mistake and say it's 20. They do 10 times as loud plus 10 times as loud and say it's 20 times as loud. It is 100 times as loud. You have to count up the number of changes of 10 you do and then multiply that. Yeah. It's 2 times the loudness, not the intensity.
You're saying 10 times as loud.
It's 10 times as intense. You're mixing the two things up. Loudness and intensity are different. Loudness is how much you perceive it to be. So if you go from 10 to 20, it'll sound twice as loud to you, but it's 10 times as intense. But going from 10 to 30 is 100 times intense. Going from 10 to 40 is 1,000 times as intense. So I'm talking intensities versus loudness.
So like these 10 to the whatever come.
Yes. Yep. However many tens you go through, 10 to that power. All right, make yourself a little note of that. The intensity goes up 10 times for every 10 decibels you go. And you don't add them, you multiply those 10s up. Because if you think about it, 70 is 10 times more intense than 60, and 60 is 10 times more intense than 50. So that's 10 times 10. Yep.
Intensity is just the surface area of the sphere, right? The sound wave?
It's, well, it doesn't necessarily have to be spherical. If we have some sort of focused sound that's not going out and not decaying off spherically, then not necessarily. And they'll do that. They use that as like they can focus a sound in one specific direction, so it's not going in all directions. So it sounds really loud to people in front of it, and the people behind it don't really hear it. You know, so it doesn't necessarily have to be that. But yes, it's the intensity is per unit area. Yep.
So then from 50 to 70, it will be 100 times more intense and
Yep.
4 times more loud? Or does it not work out?
Yeah, it should be 100 times more. Is that right? Are we thinking of that right? 100 times 10 times 10, 2 times 2. Yeah.
So for like loudness, normally when we talk though, it's always like projected in one direction. When would it be more spherical?
It's kind of an approximation. Yes, we do talk this way, but even once it leaves here, maybe it's leaving out hemispherically. And the only reason it's not going out spherically is because, you know, you have something blocking it, which is like the back of your head, right? We don't really focus it. Even if it leaves like a megaphone, it starts going out like that as well. it kind of, focuses it in one direction, but then it spreads out like that as well. It's not an easy thing to get it to just focus in one specific direction, but you can, like, you ever been to Mosey Museum of Science and Industry in Tampa?
I don't think so.
All right, well, they have these two big dishes set up outside the front of it, and they look like big satellite dishes, and they're set up like this, far away from each other, like, I don't know, 50 yards apart. And then they have a little ring in the middle where they say, talk into that ring, and the other person can go to this other one and they can put their ear right there. So, they have their little ear there, and you're talking here, blah, blah, blah. And what happens is it goes out spherically from there and hits, and it actually, because this mirror, this little thing here is parabolic shaped, it actually shoots it in a very tight beam over to there, and then it gets focused right to that spot. And even if you're whispering, they can still hear you.
Oh, okay, that's interesting.
So things like that, where you're, when you speak it, it goes out that way, but then it gets focused and stays pretty narrow.
That's what I was thinking.
They have those at playgrounds?
It was a microphone, but it was like underground.
Yeah, they're like drum roll
Oh.
playground. You like talk to them.
'Cause I think that was through tubes, right? Not through this. But
It's not the same thing, but.
Yeah. this is more like how a satellite dish works or a spotlight. Yeah,
So would whistling be the same thing as talking?
yeah.
So even though it's like more focused there,
It's still probably going to go out pretty close to that, right? If you wanted something, like that, except for where my hands block it in that direction, it's going out spherically in every other direction. So it's a very good approximation even for that kind of stuff. Okay? Physics, honestly, physics is all about approximations. We really can't solve hardly anything exactly. And even then our models are pretty much approximation. So if you ever want to get really good at physics, get really good approximations at approximating. It's especially the higher you get, it's all about finding those approximations. In fact, let me pause this for a second, even though this stuff. Talk for hours and hours on this. All right. So, sorry, any questions on this? The decibel scale, this intensity thing? Oh, I started making. All right. So, for the next part, the Doppler effect. We should all know this one. That's that, right, when something goes by. It sounds much higher pitched than it actually is if you're sitting still to it. If it's moving towards you or you are moving towards it, it will sound higher in pitch. And conversely, if you're moving away from it or it is moving away from you, then it will sound lower pitched. All right. If you want to think about why this occurs, let's pretend that I have a whole bunch of ping pong balls here, right? And I throw these ping pong balls at a very steady speed. And every single second I throw a ping pong ball at you, right? How often, once the first one hits you, how long is it going to be till the next one hits you? I throw one every single second at the same exact speed towards you. The first one hits you, how long later till the second one? And then the third one. 1 second, 1 second, 1 second. Because every ping pong ball is traveling the exact same distance at the exact same speed. So if I throw one a second after the first one, it's going to arrive a second after the first one, correct? But now let's say I take and I throw a ping pong ball at you, and before I throw the next one, I step back and throw this next one. Same exact speed at you. Is it still going to be that second between them hitting you? Why not? Because even though it's going the same speed, that second ball has to travel a greater distance, right? And so it's going to be a little bit further than a second away between each one. And especially as every time I throw them, I keep stepping back. Those are going to get spread out. So instead of hitting you every second, it might be every 1.1 second that they start hitting you. Because every time I take a step back as I throw a new one, they each have to travel that slightly further distance than the one before it. Okay? And conversely, if I throw a ping pong ball at you and then start stepping towards you as I throw them, is it going to be 1 second or less? Because each one I'm closer to you as I throw these ping pong balls, right? So the frequency with which you're getting hit by these ping pong balls, even though they're all going at the same speed, is changing depending upon how I am moving relative to you, correct? And the same thing, if I'm throwing ping pong balls at you and they're hitting you for a second, and now you start walking towards me, they're going to hit you at less than a second. Or if you start running away, like, oh, he's throwing ping pong balls at me, and you start running away, I think it's going to take longer for them to hit you. Okay? So, you know, that change that. Well, it's the same thing with sound waves, right? If you think of each crest coming out equally, if I have a certain frequency of my source, my speaker is just playing a constant sound, a constant frequency, like each ping pong ball is a crest, is a new wave, a compression coming at you, right? Well, if you're just sitting still and I'm sitting still, you hear it at the exact same frequency I'm sending it out to you. But if I start moving it away from you, you know, the speaker's here and it sends a compression, then the speaker's back here and it sends another compression, they get stretched out, right? And so if I'm moving away from you, instead of hearing this frequency with this much of a space between the compressions, now there's this much, and you get a lower pitch sound. And if I move towards you, then they get squished together, right? Another place you could possibly see this is, anybody ever been in a boat? Anybody ever been in a moving boat? And you look at the waves coming off the front of the moving boat and they're squished and compressed. And you look at the waves coming off the back of the boat and they're stretched way out, right? It's that same sort of thing. That is essentially like a Doppler shift. You're sending that wave off the front of the boat and then you're moving along with it. So it's not moving away from you and it's getting squished up. And if you're sending that wave off the back of it and then you're moving away before the next wave comes off and they get stretched out. All right, so does that make sense on this Doppler effect? Okay, good. So what we're interested in is two things here. Now, if you've done relative motion, usually it didn't matter. If I was going towards you at 20 meters per second or you were coming towards me at 20 meters per second, it was essentially no difference, right? Like if we were throwing stuff. Here it matters because here the speed of the wave is based on the medium and you're moving, both the source and you are moving relative to that medium. So it's not the same thing. You're not going to get the same Doppler effect. If you're playing a sound and I move towards you at 20 meters per second, I'm going to hear it differently than if I was sitting still and you were moving towards me while playing that exact same sound. It will not end up being identical. All right, those two situations are not the same. I will hear it differently in those two situations. Okay, so you have to be careful about that. You can't just solve it for one. It does matter who's moving. Okay, and so if you come through and you can do this, and I'm actually going to skip ahead here, but essentially this is for just when the observer is moving, and you can see it's the exact same thing except for a plus or minus there, right? This is for the observer moving away. This is the speed of sound. So V is speed of sound, and U is speed of observer. This is when the observer is moving. And you notice you get the same exact thing here as you do there. This is the observed frequency. This is the actual frequency of the source. Source frequency, and this is observed frequency. Okay, so it's just a plus or minus. Don't go too crazy on these ones. Hold on a minute, because we're going to go to one that we can use for every situation. So this is source is stationary and the observer is moving. So you essentially get this, one plus or minus, okay? I would not ever use this one. So I'm going to let y'all make your own little equation sheets, I think, for this. But I wouldn't write this one down. Not me. You can if you like. So here it is, the Doppler effect. You can see this is like off the boat. The waves are compressed on the front and stretched out behind it. So if you're in front of it, you're going to hear it higher pitched. If it's going away from you, it's that. So here, this is a moving source now, instead of a moving observer. And you look, you get something very similar, but it's a reciprocal there, right? 1 over plus or minus plus, just like that. The Doppler effect for a moving source. So similarly, you find this. And then what we can do, moving source, moving observer, you can see the comparison there. Like I said, they're not the same. Is this one. This is the one you want to know. Here you see you have a U for the observer and a U for the source. This is the one you want to use. This will work if you have a stationary source and a moving observer. It will work if you have a a stationary observer and a moving source, and it'll work if they're both moving. Like, for example, if you're driving down the road and there's a siren coming up behind you, or a siren going the opposite way from you, you are moving and the source is moving. If it is a version where the observer is stationary, this U naught goes to 0 and it's just 1 over that right there, which is what it just quickly reduces back to those previous versions we were looking at, right? That numerator just becomes that 1 right there. And if the source is stationary, then it's just 1 plus mu naught over V, which is this result right there. 1 plus or minus it right there, okay? So you just plug in all the different speeds, speed of sound, speed of the source, speed of the observer, the actual frequency into each one of these, and you can figure this all out, okay? So not too bad. What was that? So V, speed of sound, or yeah, speed of the sound, U naught speed of the observer. That's who's listening to the sound. US is speed of the source. That's where the sound is coming from. F, frequency of the source. And F prime, frequency observed. What it sounds like to you. Yeah, plus for, in the top one, pluses for going towards you away from you. Honestly, I don't even really think about that. That was the next thing I was going to say. You can try and memorize that if you want, all the different possible versions. The way I look at it is I say, okay, if I am moving toward it, then would plus or minus here make it bigger or smaller? So if I'm moving, so this is the observer. If I'm moving toward the source, it's going to get higher pitched. So I'm going to want to use plus there because that makes my numerator larger, which then multiplies by this and gives me a higher frequency, right? If I'm moving away from it, I'm going to use minus because I need a smaller frequency, a lower frequency, so it gets lower pitched, right? So you're just going to kind of use your observation. Then you look at the bottom. If the source is moving towards me, it's going to make it higher pitched, right? So what do I want to use? Plus or minus there? Minus, because making the denominator smaller will give me a larger number to multiply that frequency by and give me a larger frequency. Okay? And then the reverse, if it's moving away from me, I'll use plus because that gives me a larger denominator, which then gives me a smaller fraction number there, a smaller number out in front, and so that reduces our frequency. Is this affecting this? I keep feeling like every time I point this up here, something, is it just that flashing at me? All right. Does that make sense? So just think about whether or not it would increase the frequency or decrease the frequency, and then you should be able to tell whether or not you should be adding or subtracting it. Then you don't have to worry about the plus, minus, minus, plus thing. Okay? It's you either have to add it or subtract it, depending on whether or not it's going to increase it or decrease it. Yep.
So like the plus on the top and the minus on the bottom don't always have to go together.
No, you could have like plus plus or plus minus or minus minus or minus plus. Like it just depends. You know, like, oh, I'm driving down the road and the ambulance coming up behind me. We're both in the same direction. That's going to be he's coming towards me, so that's a minus in the denominator. I'm going away from him, so that's a minus in the numerator. Right? I'm trying to get away, even though he's coming faster towards me. It's going to be an overall increase, but
Yeah.
you know what I mean?
Mhm.
So that's minus minus. That's the way you think your way through those. I hope I just said that right. Okay. Any questions on that? How much time do I have left? Okay. Oh, plenty of time. Okay. So yeah, this is used a lot, right? You use this, you see like the Doppler radars to tell you about the rain and stuff like that, and tell you your speed, which we'll talk about here shortly, how they do that exactly. All different kinds of things. Yeah. We will. I want to do those secondary because I'm going to record them at the very least for y'all. Okay. I gotta make your test today, so I probably will do chapter 14 tomorrow. I'll try and finish up chapter 13 and start getting it loaded at chapter 14 tomorrow. Yeah.
So if something is stationary.
Or the
and
next
it's
day.
Positive, like let's say the observer was moving, but the source wasn't, would we use the positive?
So no. If the source is stationary, then US is 0, and it's just 1 plus or minus U naught over V. The whole bottom just that goes to 0, and then it's just divided by 1. And so it goes back to, where was it? This version, right? It immediately becomes that. Yep. Just put them in there. Think about your plus or minuses, and that's it. You don't overcomplicate these. The biggest trick is figuring out, whether or not they should be pluses or minuses. And that you just do by thinking about whether or not that thing's motion is trying to increase or decrease the frequency. What's that? I'm sure I would probably give it to you. 340 meters per second, 343. I mean, it depends on the temperature and the air density, and there's no exact number except for they say it's 343 at 20 degrees Celsius and the standard temperature and pressure or something like that. I'll give you something like that. I don't know if what I just said was correct or not, but something like that. Okay. So it does about 3 football fields in a second. That's about what I remember. And football fields, 120 yards, sorry. So 340 meters per second. Okay. Pretty fast. Not nearly as fast as light though. Because light could go around Earth about 7 times in 1 second. So that's way faster. That's why you see lightning before you hear it. Okay. So here, Doppler effect stuff. They can use it to tell which direction blood is flowing and stuff like that, and how much it's flowing in and out, whether or not. So for you medical people. Here, superposition and interference. So basically we can use a superposition principle here, which means you can just simply take the 2 individual waves. You can count crests as positive numbers, troughs as negative numbers. And if you want to know their overall amplitude when they go over top of each other and interfere, you just add them together. So if we look at this one and we're like, oh, this one is 1 meter high and this one is 2 meters high, what's going to happen when they meet each other? Any guesses? 3 meters, right? It'll be 3 meters high, okay, like that. And the same thing, if we had like a negative 1 meter here and they met, what would we get? We'd get a positive 1 meter, 2 meters minus that 1 meter. All right, so that's really all that's going to happen there with those. It's just superposition. You can do them individually and then combine them together, almost like adding 2 different functions together. That you have a function that's some wavy thing and you add another function to it, they just add up, right? However they overlap, you just add them all up. The two graphs just add. All right, and here you can see this more with the interference. Waves are really neat because if you look at them, they come along, they interfere for a moment while they're overlapping, and then they go on their merry way and come right back to what they were. It's always was kind of fascinating to me. So here you have 2 wave crests coming in. You can see they're on the left. They get closer to each other. They combine, they make that 3, and then they go right back to what they were. But you notice that this one is now over here on this side, and it continues on about its merry way as though nothing happened. It'll come right back, okay? And then they just go on. And this is the really neat one I always thought was fascinating is you look here, we've got 2 waves that have the same amplitude, but one is a crest and one is a trough. And look what happens in that middle picture, that middle one right there. If you came up and looked at it at that moment, you'd think there was absolutely no wave or energy there, right? Because it would have been down at 0 if you snapped a photo of it. But a moment later, they both reappear and continue on their merry way as though nothing happened. To me, that was always so cool because you would think, to me, it just seems like they would come along and hit and just cancel out and that'd be it. It'd be done. But they don't, they reappear. They come back out after like totally canceling each other out and they come back. And light does this. Light acts like a wave and light will go through. You can totally cancel it out and then totally have it come right back. It's, I don't know. To me, that's really fascinating and feels like something that shouldn't happen. Doesn't it seem like something should be able to just disappear and then suddenly they reappear like that? I don't know. Is that just me? Am I the only one that's fascinated by that? Huh? Pretty much just me? Thanks. Oh, I thought you said it was pretty much just me. Oh yeah, totally you. You're the only one that finds this interesting at all. Keep going. All right. Here, I'm not sure what these are pointing to. It doesn't look like they're pointing to the right things to me. If you look at these two dimensional waves here, you can see if you count the circles as the compressions and in between them as the stretches for sound waves, you can see here, this one looks like it's pretty much pointing at a good place. I would think you'd look here and you'd say, like right here, I have a crest or I have a compression meeting a stretch. And so they would cancel out. But then like right here, you have two compressions getting together. And so it's going to make a high pressure area there. They're going to combine. And so what you can see is all through here, you can find places where it's canceling out and not canceling out. If you have these two sources that happen like that. And so you get a bunch of areas where it cancels out and doesn't cancel out. And you've probably all experienced this at some point, right? And I'll tell you about it in just a minute here. So, and it's more like right here. So what you can do is look at this, you have two sources coming, like these are two sound sources. And if they are the same exact thing, right? They're all, coherent and they're all in phase with each other. What's going to happen is if you're the exact same distance away from both of them, like at point A there, it's going to meet constructively all the time because the compressions from each have traveled the exact same distance and therefore are always going to be in the same phase, right? But if you go to a location where one of them has traveled exactly either a half a wavelength or 1.5 wavelengths or 2.5 wavelengths, some half integer wavelength version of the wavelength away, then one of them is going to be a compression and one of them is going to be a stretch, and they're going to cancel out every time. And then if you go to a place that's twice, so this would be like they're off by half a wavelength. This would be off by a full wavelength, and they'd be back to being in phase. And you'd get compression and compression or stretch and stretch, and they would combine constructively. And so if you were to walk along here, you would hear the music be, say this was music or something, you'd hear it loud, then it'd get softer and you wouldn't hear it, right? If it was just, not say music, because music has a bunch of different frequencies and it would change, but let's say it was a single frequency of two things emitting the same source. You'd hear it real loud, then you wouldn't hear it. It'd get soft, you wouldn't hear it. Then it'd get louder and you'd hear it again, and then softer and louder and softer as you went between whole integer wavelength differences and how far you are from each to half integer wavelength differences. Does that make sense? I see some nodding and some blank stares. Does that make sense though? In fact, you probably have experienced this in your car. You ever been driving along and maybe you stopped at a red light or something and the radio station went out and you pulled forward a few feet and suddenly it came back? Anybody ever have that happen? Some of you? Yeah, that's because typically what is happening is, it's not that there's two sources in that one, but rather what's happening is you have a single source and then you have something like a building here. And so that same source is coming over here, bouncing off the building and coming back over to you. And if you happen to be at one of those places where it was a half integer one, your radio just suddenly kicks out because it's destructively interference, because the radio isn't sending out different sound frequencies to you to make the difference. Each radio station is broadcasting over a specific frequency, right? 97.9 hertz or 100.7 hertz or whatever they are, right? Huh? Yeah. You change stations, you're changing which frequency you're listening to. And so if you're at a place where you're at one of those half integer wavelengths of that specific frequency of radio wave, and it's bouncing off over there and doing that, it can interfere with itself and knock itself out. Right? Especially if you're in like a downtown of a city, it's going to happen more often there because it's going to go in and out as you drive through those things.
Could you say like this is like public
Yes. Yes. But those I think are typically done on microwaves and not the radio waves. So they're a little longer in wavelength, or a little shorter in wavelength, sorry. But yeah. Yeah. In fact, take a, well, no, I'm not going to get into that. Never mind. Never mind. I wanted to tell you about you could like melt a plate of cheese in a microwave if you didn't let it turn, and you could see where all the constructive and destructive interference happens. That's why they make the microwaves rotate now. Now, probably your whole lives they've been there. They didn't do that originally, but they make them rotate because there are dead spots inside there where the microwaves interfere and cancel out. And so if you set your drink or something in there and it didn't move and you happen to set it in a dead spot, it wouldn't get heated up really. So now they move it through so it goes in and out of the dead spots as it rotates. I can't tell if y'all are like laughing at me or like, actually, this is pretty cool. I'm not sure what's going on up here. I'm going to pretend like it's the pretty cool thing. Okay. And then lastly, I think that's all we have left to do. Standing waves and then beats. Okay. Man, I could spend like a week on standing waves, like nonstop. These are so cool. This is why you get orbitals, all you chemistry people. This is like the foundation of your orbitals, your electron orbitals and their shapes and stuff. Like this is it. I'm not kidding when I say I think I could teach an entire semester on just this. It's so much fun. This is so cool. So this is standing waves. All right. So the idea here is if you start with a string or something of a fixed length and you start to vibrate it, right? At first, you just start doing it real slow and you get kind of a jumbled mess on it. Nothing really works. And if you just keep going and you slowly start to increase, right? You start to do this faster, you're decreasing that period, you're increasing your frequency. What's eventually going to happen is it's going to start to look like this as it goes up and down in the middle. Almost like a jump rope. Really nice, right? If you don't do the jump rope at the right speed, at the right thing, it doesn't work. You get like a jumbled mess. But if you go at the right pace for it, you get that nice thing. And so you get this nice up and down. And so that's going to be your first little standing wave. That's going to be your fundamental frequency for that string. And in fact, this is also what makes like stringed instruments and stuff make different sounds. And so you would do that. And then this would be the actual note you're playing. Then, if you keep going a little faster than that, it goes back to being a jumbled mess. And then you keep going faster and faster, and eventually you get a next nice wave. Where's the picture for this? Like that one right there. And it'll start to be real nice. This side will be up, the right side's up, the left side's down. Then they go down, then the left side goes up and the right side goes down, and they do like that. They alternate like that. And you'll see, and it'll do like that. And it's really kind of cool. And then you go a little faster and it goes back to a jumbled mess. And then you keep going faster and you eventually get one like this, where the middle is up and the two outer edges ones are down. And then the two outer edge ones go up and the middle one goes down. So you have like this kind of a thing going on. I don't know how to do that very well. I don't have free hands. So, but that ends up happening. Okay. And then it goes to a jumbled mess and then you go faster and faster and then you end up with 4 of those things on there. Right? And it starts to look like that. And the math we get for this is this right here. This actually comes from V equals F lambda. And if you look at this string, if we come back over here, we can solve this for F. F equals V over lambda. Take a look at this first one. This one right here, right? What's the wavelength of that? If the length of our string is L, what's the wavelength you see right there? Huh? I can't hear you. Nope. How much of a wave do you see there? Huh? Half. So what's the wavelength? 2L. This is half a wave. Here's the full wavelength. This is the full wavelength. It's 2L. So if we come back over here, we can replace that lambda with 2L and it's V over 2L. This is our fundamental frequency. That's it right there, V over 2L. Go to the next one. Oh my gosh, I'm out of time, huh? How much of a wavelength is there? That's 1. So you come back over here and it's V over L. And then there's that 1.5 wavelengths and so on and so forth. And you end up with this right here. NV over 2L, where N is integers, 1, 2, 3, 4, 5, 6, 7. And those are all of the standing waves that you get. Think back to that Tacoma Narrows Bridge. Did you see it doing that? One side would be up, the other side would be down. Do we need to watch that video again? And the middle stayed pretty stationary. In fact, if you come back here to these and you put your finger right there in the middle, it's going to be just fine. It's not going to get hit. Anybody play like guitar or something? Anybody ever play a string and you play harmonics where you lightly touch your finger in a spot? You ever do that? Think about this. If I lightly touch my finger here in the middle, I'm going to cancel out this one, and I'm going to cancel out this one over here that have an amplitude in the middle. I'm not going to get that one canceled out. So I end up with this one staying and those two going, and it changes the sound. We'll start from here next time. Sorry, guys. Have a good one.